Hello everyone, today we're talking about matrix operations, material from 2.1. So the basic idea is we want to today talk about how matrices themselves can be thought of as algebraic objects. We'll see that they can be added and even multiplied. So first some notation. Let's suppose that A is an m by n matrix. We're going to let Aij denote the entry in row I, column J. So, I have my matrix here. This is A. And in row I, right, I've got something, and in column J, and that's the entry Aij. That's what I mean when I say Aij. Okay, so we're going to use that kind of throughout the lecture today. Okay, so what can we do with the matrices? The first thing we can do is add them and scale them coordinate-wise as we did vectors themselves, right? So we can add matrices and scale. So add two matrices and scale. Let me just do this by an example. I should say this is going to be coordinate-wise. Like I said, as we did with vectors. So for example, let me take A to be, 4, 0, 5, minus 1, 3, 2. B is going to be, say, 1, 1, 1, 3, 5, 7. Let's take C to be a 2 by 2 matrix, 2, minus 3, 0, 1. So what can I do? I can take A plus B, and the reason I can add these two is that they have the same shape. They're both 2 by 3. And what I do is I just, I get a new 2 by 3 matrix where I add the entries. So this would be 5, 1, 6, 2, 8, 9. And, all I did here is I took 5 plus 1 because I took the corresponding entries from the two matrices A and B and added them together. Okay. Notice that A plus C doesn't make sense because they're different shapes, right? I can't actually add coordinate-wise because they sit in different places. It doesn't make sense to add those two matrices. And what else can we do? We can also scale matrices. So what about like 3 times B? Well, this would be 3 times 1, 1, 1, 3, 5, 7. So again, coordinate-wise, I just scale everything by 3 that I see. So 15, 21. And for instance, this is just 3 times 7 because I scaled that entry. Okay, so again, usual story. This is how we added vectors and scaled vectors. The properties that they satisfy, I'm not going to list them all here, but I'll let you check the book. So see the book for the full list. But for example, you have something like a distributive law that says if you take the sum of two matrices and scale them, that's going to be the same as taking the sum of the two scalars, and I'll just say etc. So, okay, so that's the idea of matrix, adding two matrices and scaling a matrix. What we want to focus on today is the maybe more interesting example of multiplying matrices. Can also multiply two matrices, I should say, under certain conditions. Well, in certain conditions on their size. Okay, so to motivate this thing, to motivate this idea of matrix multiplication, the motivation comes from composition of linear transformations. Okay, so let me explain what I mean here. So composition is, you've probably seen this again in your pre-calculus class, where you take two functions and you do one then the other, basically. In our context, right, our transformations are moving between R somethings, right? So suppose I have an RP here, an RN here, and an RM, right? These are, this could be R2, R5, and R3 or something. And what we know is that if I have a matrix, say B, that is going to be, right, this would have to be n by p. If I have a matrix that's n by p, it'll eat a vector x, and it'll spit it out over here as b times x, right? So remember, I input a vector that has p entries. I can multiply it by a matrix that's n by p, and it gives me a vector that has n entries. Okay, but then I can keep going. I'll go one more time, and suppose I have a matrix here that's, so this should be m by n. And this is a vector now in Rn. I can apply a to this, and I get a times bx. Okay, and this is going to be a vector in Rm. And so what I want to say is that this vector here, this is a times bx. I want to say, basically define that this should be the matrix AB times x. But what should this matrix be? That's what we're going to actually now kind of decide. Okay, so what is the matrix that does this, this is what I mean by composition. It does one, then the other. First B, then A. So let's see. Let's actually figure this out. Suppose, as usual, let me give this some names. So suppose the columns of A are A1 through AN. The columns of B are B1 through BP, I guess, where we have B columns. Then what do I know? And let me also let x be, x lives over here. It has P coordinates. Okay? Okay, so let's go through this calculation. Then what do I know about B times x? So if I start with x, this vector in RP, what we know is that B times x, right, by definition, when I take a matrix times a vector, this gives me a linear combination where the weights are coming from the entries of that vector, right? And the linear combination has vectors coming from that matrix B. So that's the definition of B times x. But then what's A times B of x then? Well, this is A times all of this, right? This stuff here. But notice that A is a linear transformation. So what happens when I take A times the sum of, a bunch of vectors? This is going to be the same as A times x1, b1 plus A times, x2, b2, dot, 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 A times xb, xp, bp, okay? But then remember, when I take A times the scalar of a vector, this is the same as x1, ab plus dot, 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 up through xp, abp. Okay, so what do we see here? We see that when I take A times this vector, what I get is a new linear combination, right? The weights are, again, those x's that came in the vector. But now the vectors that are forming this linear combination are actually, right, these vectors, AB1, AB2, etc. So what we're seeing here, the punchline, is that, this vector that I'm getting, make sure you can see this. So this is implying that this thing that we want to declare as AB times x, which we know is A of bx, is actually of the form, right, matrix times vector, where the matrix is AB1 as the first column, then AB2 as the second column, up through ABP as the last column, times the vector x. Okay? Because that's again, the definition of matrix times a vector is just you take that linear combination with those vectors and weights coming from the vector x. Okay, let me write that down. So what do we just prove here, basically? So fact, then, that we kind of, fact / definition, says that suppose A is an m by n matrix, B is a n by p matrix with columns, let's say, B is going to have columns B1 through BP. Then this thing AB is an m by p matrix, right? Remember, AB is mapping from RP. It's eating vectors in RP and spitting them out in RM. So it better be an m by p, right? Eating vectors in RP, spitting them out in RM. It's an m by p matrix given by, what we just said. So AB, repeating myself here, but it's going to have columns where the first column is A times B1. That's a vector, right? And then I just do that for all of the columns of B, and I get the columns of AB. Okay, so the columns of AB are given by taking the matrix A times the columns of B. That's the fact. Okay, so let's do this with an example. Let's take A to be 2, 3, 1, minus 5, B to be 4, 3, 6, 1 minus 2, 3. Let's determine A times B. Okay, so what what do we do here? So again, the rule says that I need to I need to compute 3 vectors basically. I need to compute A times B1, A times B2, and A times B3, where this is B1, this is B2, and this is B3. Okay, so let's do that. I'll probably do one of them for you, and then take my word for the others. So what is A times B1? Well, it's 2, 3, 1 minus 5 times B1, which is 4, 1. And we know how to do matrix times vector, right? So this is going to be another vector of length 2. It's going to be 8 plus 3, which was 11. And then this entry will be 4 minus 5 minus 1. I'll just tell you that AB2 is, see, I did this over here, it's 0, 13. A times B3 is, if I did it right, 21 minus 9. And so what do? Is you just take those vectors, right? I did that for every column of the matrix B. And now I just put them all together. So this implies that AB is, just stick all those in there. So this will be 11 minus 1, 0, 13, and then 21 minus 9. So it's a 2 by 3 matrix. That's what we expect. And that's what you get. That's the product of those 2 matrices. Let me just point out, I won't write this down, but we saw this already, that in order to make sense of a matrix times another matrix, you need, so maybe just go back to this definition, you need that the number of columns of A is equal to the number of rows of B, right? If that's not true, it doesn't make sense. So just note, I will write this down, I guess. AB makes sense only if the number of columns of A equals the number of rows of B. Okay, and so also notice that AB is going to be different than BA, just because you can see this already, just because of the shapes of the matrices, and we'll have more to say about that next time.